All right. Anybody have any questions about the vector assignment? There was one thing, actually, now that I remember, that someone brought up. There were two of the questions that referred to like numbers 5 and 6, and they were misplaced by one number. Hopefully you figured that out. But the one that said in question 5, blah, 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 should have said in question 4. And the one that said in question 6 should say in question 5. Okay, so here's what we're going to do with the exams. I am going to change that exam thing a little bit. So here's a change to the syllabus. Before it said we were going to have those 4 exams. They would each be worth 15% of your grade, so a total of 60%. And then the last exam would be optional and would make up one of those other 4. Instead, we're going to just have 5 required exams on each of the Fridays. So 5 cumulative exams. Cumulative up to that point. These 5 are worth a total of 60% of your grade, so now each one is only worth 12%. And we'll just double count that 5th one, so you'll get a score on that 5th one that's worth 12% of your grade, and then I'll also replace your lowest exam score from the other 4 with the final. Okay, if your final's lower than those other 4, then I'll keep the higher. But you can use exam 5 to replace the lowest score of exams 1 through 4. Okay, does that make sense to everyone? Yep.
So exams are required now, right?
They're all required now. Yeah, that's right. But so still, if you miss one, then you won't make up that exam specifically, but your score for the last exam will replace that 0. You know, so you can miss one exam and still make it up. Okay. Okay, so where we left off last time was talking about unit vectors. So we talked about how to calculate unit vectors when you know the vector, know an angle that the vector makes with some reference line. But what we haven't done yet is talking about how to calculate a unit vector pointing in the direction from one point towards another point. So a unit vector in the direction of a vector from one point to another one. So if you want a vector pointing from the point A to the point B. Define a vector v. This is not a unit vector. That's equal to the coordinates of B minus the coordinates of A. And so that gives us a vector that's in the right direction, but it doesn't have a length of 1, and we need to make it have a length of 1. So then we'll calculate the length of that vector. And yesterday we talked about how to calculate the length. That would just be the x component squared plus the y component squared plus the z component squared, all square root. And then the unit vector, so v hat is just equal to 1 over the vector length times that vector v. So you can think of that as, you could also write this as the x component is the x component of v divided by the length of the vector. The y component is the y component of the vector v divided by that same square root expression. And same thing with z. It's equal to vz divided by square root expression. So here's an example. So let's say that there's a bar connected to the wall, and in whatever coordinate system we're using, the coordinates of this point are 2.51, and the coordinates of the point where it attaches with the wall are 4.52. So given a cable tension T, what's the force vector the cable applies to the bar? Well, we know that the force that the cable applies to the bar is parallel to the cable, and it's acting away from the bar. So we know that it's directed like this. And so what we need to do is, we know that it has a total force magnitude of T. We need to figure out a unit vector in that direction so that we can multiply it by T to express the total force vector. So this is what we're trying to represent, a force vector with a magnitude of T pointing in that direction. So the vector V, first of all, we're going to get a vector that's in the correct direction, but doesn't have a length of 1 yet. That's going to be equal to the destination point minus the starting point. So 4.52 minus 2.51, and so you get 2, 1, for the vector v. The length of that vector is 2 squared plus 1 squared square root. So that's root 5. And now the unit vector is our vector v divided by the length. So it's equal to 2 over root 5, 1 over root 5. And so now that we know this, we know that the force vector is equal to t times that unit vector we just calculated, which is 2t over root 5, t over root 5. And I mentioned last time, a lot of times with two-dimensional problems, you kind of have your choice. You could figure out a way to calculate your unit vector based on angles, or you could figure out how to calculate it based on points. Once you go to three-dimensional problems, you really don't ever want to try to figure it out based on angles. You just need to figure out coordinate points and use this approach. So you're going to have to get familiar with this approach. Okay. Anybody have any questions about that right now? Yeah.
The forces, the points that you're like 4.52 and
Yeah.
5.1, those are coordinates, right?
Yeah, and those are, that's right. They're coordinates, and they just are given in this.
So then how do you get a force from just coordinates and torque? Is that
We're using those points to figure out. So you can think of this as, this is the vector v. Okay? It's a vector that starts at this point and ends at this point. And so it's in the direction of the force, because that just happens to be what cables do. But it doesn't have the right length, because this vector v has a length, as we saw later, of square root of 5. So we just have to divide by the length, and it ends up giving us a vector that you can think of as just a pure direction. And then you multiply the, and then you multiply the magnitude of the force, the tension, to that pure direction, and it gives you a vector that has both the correct magnitude and the correct direction. So yeah, think of this approach as really separating it up into, separating this force up into just the magnitude and just the direction. That's what unit vectors let you do. Any other questions about that? Okay, I'll leave that. Okay, let me give you one to work on, and you can, if you get stuck, you can ask me questions, bounce it off the people next to you. This is something I'd like you to get in the habit of doing. I'm going to give you problems, from time to time in this class, and I'd like you to just get used to try to get through the problem, get through what you can, show what you have to the person next to you, and then if the person next to you doesn't know what's going on, you can go, "It's ridiculous. Hey, everybody, look at this." No, don't do that. So here's the problem. So let's say that we have we're given that this surface makes an angle of, what does that look like, 60 degrees? Makes an angle of 60 degrees with the horizontal. And then let's say we have a vector that makes an angle of 15 degrees from that surface. And so in this coordinate system, You see what I'm trying to get at? This is solid. That vector is coming out of that surface. What's a unit vector? And actually, let's make this part A. First, what's a unit vector? In the direction of the force. So this is the force, call it F. And then second, if the magnitude of the force is 100 newtons, what are the force components? Okay, so I think this is an approach to these that always makes it easier. So here's the coordinate system. Like eventually all this stuff you'll sort of do in your head, I think, but this is the thought process for all of these kind of problems. So here's the coordinate system. And now just draw in all the relevant lines and draw in all the relevant angles and put any vectors put their tail at the coordinate system. So I'm going to draw, so here's the ground. And then the vector is put its tail at the coordinate system, and it's like this. We know that this angle is 60 degrees. We know that this angle is 15 degrees. And so now I'm just going to hop around in steps from one thing I know to another thing I know. If I go counterclockwise, it's positive. If I go clockwise, it's negative. So I'm going to go, well, let me make both of these two vectors also. So how am I going to do this? Okay, watch this color coding. This is going to be so great. Okay, so change this one to orange. This one's red. Okay. So starting at the positive x-axis, we go 60 degrees to get to the red vector. Then we go 180 degrees to get to the orange vector. And then we backtrack clockwise 15 degrees to get to the black vector. And so if you add all those up, you get 225. And so then the unit vector is equal to cosine of 225, sine of 225. I don't have that written down. Can someone tell me what those values are? Oh, yeah, duh. I've only seen that angle before like 100 million times. And this is also. Okay, maybe not 100 million, but a lot. Okay, so that's the unit vector. Anybody have any questions about that?
Is this just something that becomes like second nature after doing it a couple times?
Yeah,
Okay,
right.
So I was like, wait, what? And then
Right.
I'm like, oh,
But
sure,
yeah, if you can make sense out of those steps, I'd say, just go through it slowly, as long as it isn't second nature, and eventually Muscle memory just kind of takes over. But in a lot of 2D problems, we'll have to do this kind of stuff.
Okay, gotcha.
Is there a reason why you went from 60 to 180 and then backtrack?
Well, just because it's 15 degrees between, it's not 15 degrees between the red and the black. It's 15 degrees between the orange and the black. Do you see what I mean?
We don't multiply that by
That's what we're going to do for part B. So this would be part A. The unit vector you don't. And then to get the total force, that's equal to the magnitude times the unit vector and so that's negative 70.71, negative 70.71, and that's a force, so units are newtons. Sorry, Mohammed, did I cut you off?
No.
Okay, got it. Any other questions? Yep.
So you like it and to leave it in the bracketed form because it asks for the components?
Oh, yeah, that's, I don't, you can write your vectors however you want, I guess. That's all I meant is write it in the component form. Yep. But if you wrote it out in IJ form or whatever, that's fine with me. This way of doing vectors, by the way, the reason I use it is when you start doing matrix manipulations with vectors, this form is helpful, but it's only one more step to go from whatever form you prefer into this to do the matrix manipulation. So, it's not a very big deal, but this is a nice form for some kinds of calculations. Any other questions about that? Okay. Well, that's the end of the vector review. So now we're going to go on to statics of particles. And if you remember Physics 1, this is sort of following the rough path that you took in Physics 1. We're going to start out by doing calculations with particles. Then after we get comfortable with that, we'll change to rigid bodies where you have to introduce moments. So statics of particles. What does it mean for something to be a particle?
no dimensions but mass.
That's exactly right. So a particle is an object with mass but no length dimensions. And since it doesn't have any length dimensions, there's no such thing as orientation. Excuse me. Excuse me. I'll edit that out of the video. So, therefore, we don't worry about a particle's orientation. If it's moving, the idea with a particle is that there's no way to differentiate between the different orientations. You know, in order for the front to look different from the back, you need to have some kind of length that lets you differentiate. And so to us, there's no difference between something being upside down or right side up. And since we're not worried about the particle's orientation, we're not going to do anything with the rotational Newton's second law. So no Rn2L, no moments or anything like that. Moments only happen because forces are acting on an object at different locations. Particles don't have any different locations. One thing to notice is, so usually particle physics is used for really small objects, things that do have very small length dimensions, but that's not necessarily the case. And you use particle calculations for the motions of planets, and those are huge. All that really is required for you to do particle analysis of an object is that you don't care about the orientation. So you can use a particle approach for any object where you don't care about its orientation. As long as you consider the particle's location to be the object's center of mass. So as long as the particle's position is taken as the object's center of mass. And if you think about, like I said, when you're talking about planetary motion, you use particle physics. So what if instead of tracking the motion of the center of mass of some planet, you decided let's do something a little different today. Let's track the motion of this point as the object moves through, moves in its orbit. Well, this point is going to actually follow some crazy path like this as it goes around, which would look like it wasn't satisfying Newton's second law, given the gravitational forces that are acting on this planet. That isn't what you would expect for a particle. The reason it wouldn't work is because you'd be treating the particle's location as a point other than the object's center of mass. So you got to follow this. So if you track that, it does exactly what you'd expect it to do. Since we don't care about orientation in particle physics, the only laws of motion, equations of motion, are Newton's second law. Which says that the net force acting on the particle is equal to the particle's mass times the acceleration of the center of mass. This equation is actually two equations in 2 dimensions and 3 equations in 3 dimensions. In the static case, so if the particle is at rest, or if the particle is moving with a constant velocity, then the acceleration of the center of mass is equal to 0. That's what we call equilibrium. And we get the particle equations of motion in statics. Newton's second law becomes the net force acting on the particle is equal to 0. Okay, so for a particle, that's the requirement for equilibrium. And so normally using Newton's second law, you have to know the mass of objects and all that stuff. We don't have to know the mass of the object. Well, usually we'll have to figure out what force gravity is applying to it. But if we know all the external forces acting on it, the mass doesn't come into it. In this class, and in every class after this, and in every day of your job after that, and in every day of retirement after your job, every time you use Newton's second law, and or the rotational equation, you must draw the associated free body diagram. And I'm going to abbreviate that FBD, free body diagram. I think I mentioned yesterday, to me, this entire class is about learning to draw good free body diagrams. That's the main thing about this class, so it would be sort of odd if I was going to let you opt out of drawing free body diagrams. So let me give you a set of steps for how to draw the free body diagrams that I want to see, and these are pretty universal. There's nothing unusual that I'm saying. This will carry you through forever. So steps for free body diagrams. The first thing you have to do is choose a body or a collection of bodies or part of a body to isolate. What makes a body acceptable for isolating for Newton's laws? You have to be able to fully isolate it from its surroundings. I mean, not physically, but you have to be able to imagine a closed, like, shrink wrap separating what you're isolating from the rest of the world around it. Okay. So, and this can be a collection of bodies, part of a body, as long as you can imagine, basically as long as it's an object with some defined amount of volume. It has to be, or some amount of area in 2 dimensions. It has to be a chunk of material. Second, draw a closed outline of the body. And so it's important that you draw a closed outline of the body and not like a stick figure type thing of the body, because you're trying to be very clear to yourself where the surfaces of this isolated thing are. And it's also important that you don't put any external objects in your outline. The whole point of drawing this outline is to be totally clear of what you're isolating from the rest of the world, and only include that in your free body diagram. So no external objects. Okay, so let's say, so here's a car sitting on the grass, and there's a cat sitting on the car. Ooh, it looks like Batman. Satan's sitting on my car. Okay, so free body diagram. Okay, and your car has windows and stuff. So the free body diagram of the car is like this. Okay, it's an outline of the car. There's no details about the inside, what's inside your boundary, and there's no inclusions of anything that's outside of your boundary. It's just the boundary. Okay. So some of the things you don't want to do. So this is, yes. Okay. No. And that looks pretty good, right? No! The grass is not included. How about this? This doesn't look so bad. No! Because the windows are internal to your boundary, and so you don't want those drawn. All you're trying to do with this diagram are be perfectly clear about the boundary between your chosen object and the rest of the world. Okay? Yeah. In a way, I suppose you could, unless you're talking about like subatomic particles or whatever, kind of everything is a collection, So yeah, we don't even really have to make that distinction. As long, you can choose clumps of stuff, collections of stuff, as long as you can imagine, as long as it's a contiguous amount of material that you're isolating. The third step, draw all the loads applied to the chosen body by, let's say, external objects. That's lucky that we only have to deal with the external objects, because if you think of this as, like you said, a bunch of wheels and a bunch of windows and a bunch of whatever, each of those things applies forces back and forth to each other. We'd be here all day. And if you think of it as a collection of atoms with subatomic particles, and you're going to try to draw all those forces in, good luck getting physics done. But the only thing we care about are the forces that are applied to the chosen object by the outside world. Okay. That can sometimes be a little, like you look at a problem, a complicated problem, it can be a little bit daunting, like what are all the forces? But it's easier if you just kind of try to be disciplined about reminding yourself that all of the external loads applied by outside objects are either first field forces, and that's kind of being unnecessarily broad most of the time. Field forces would be like magnetic fields, electric fields, gravitational fields. In this class, the only fields we have to worry about is gravity. So just the weight for us in this class. And then, so once you've drawn the force vector applied by the weight, the only thing that's left is contact forces applied where the outside world touches the boundary. Okay, so if we think of the example we just did, there's kind of a lot of stuff going on in that picture. So where are the external loads, or what are the external loads that we have to worry about? Well, first there's the weight, and that acts at the center of mass, down. And now that we've dealt with the weight, there aren't any other field forces, all we have to do are mentally go around the boundary and look for places where the outside world is in contact with the object. So there's one here, there's one here, and there's one here. So there's an external force applied by the cat. There's an external force applied by the grass on the front wheel. And then there's an external force applied by the grass on the rear wheel. And once you've mentally gone around the boundary and found all the places where the outside world is touching the boundary, you know that you're done. The last thing we have to do is just figure out how to represent these forces, and that's a lot of what this class is going to be about. But I'll give you a little more detail about that right now. All forces can be broken into forces with, and actually let me change this forces to loads. The only difference between forces and loads is loads also include some moment things that we're going to do when we start talking about rotations. So loads are forces and also moments. So all loads can be broken up into loads with known directions and loads with unknown directions. And in the free body diagram, we're going to treat those two things a little bit differently. If you know the direction, then in your free body diagram, you're going to draw an arrow in that known direction. And then associate that arrow with a scalar variable or a number. The idea is that if you know the direction of a force or a moment, you don't need variables representing the direction. Those are already known. So you show the arrow showing that direction, and then the stuff that you have to figure out just has to do with how big that load is. So the scalar variable or number just represents the magnitude of the load. For example, if you have a mass that's hanging from the ceiling, the free body diagram looks like this. Well, you have mg acting down. And then you know that the cable applies a force away from the chosen body, parallel to the cable, so you know the direction. And so you only have to associate that force with the scalar variable. In this case, I'm calling it t. Okay, that says that there's only one variable you still have to solve for, and that's how big the force is. If you don't know the direction of the load, then associate don't write that. If you don't know the load direction, draw small coordinate axes and associate that with a vector variable or a constant vector, a known vector. Okay, so for example, in the case above, so we have this car on the grass. The cat's sitting there. A free body diagram of the car has the outline. There's the weight. And then if we assume that we don't know anything about the type of force that the ground's applying to the wheels or the cat's applying to the hood, we would write this as coordinate axes associated with F. I'll call that F for front. Over here, these coordinate axes are associated with the vector FR for rear, and here it's associated with the force applied by the cat. And those aren't really coordinate axes. You know, you only have one coordinate system. But these just tell you what directions the components are pointing in that you're trying to solve for. Okay, so this is saying you have one component going horizontal and one component going vertical. Any questions about that?
This might be a dumb question, but you have two arrows pointing forward. Is the car supposed to be moving forward? Or three arrows pointing forward?
No, that's just saying we don't know what those values are, and it might turn out when we solve for it that the value associated with that horizontal component could turn out to be 0. Or if it's not moving, then this one might have a horizontal component that's positive 10, and this one might have a horizontal component that's negative 10, so they cancel out. It's just saying we don't know anything about that force, so we're leaving it as open as possible to having component values. All right. Any questions, other questions about that? Yes?
For the forces, couldn't we just draw it as, like for the force of the cat, couldn't you just draw it as an arrow going down instead of a...
You're right about that, your intuition on that, but for now I'm going to just pretend that we don't know anything about what those forces are, and I'm just being as general as possible. But yeah, you're right that if we went through all this formal stuff, we'd see like, yeah, the cat's, it's only an upward force applied to the cat. And the cat, on the other hand, is applying a downward force to the hood. Any other questions? All right, well, let's take a 10-minute break. We'll start again at 10 after 2, and we'll start using free body diagrams in calculations.